Hi, I'm Leonardo, and I'm going to present the development of a UVM environment for the functional verification of a network-on-chip router. Now, a quick introduction about SoCs and NoCs. SoCs, or systems on chips, they integrate multiple systems like CPU cores, memory, bus, peripherals in one single circuit. And NoCs, or networks on chips, they are an alternative to the conventional buses that was being previously used in SoCs. Now, the advantage of using a NoC is because of throughput data and data concurrency. Because of the architecture of a NoC, data concurrency is much better in a NoC than in a conventional bus. Now, a NoC, as you can see in the picture in the right, is composed by routers, links, and adapters. So the purpose of this work is to verify the router of a network on chip using UVM. UVM stands for Universal Verification Methodology. UVM is the most widely used methodology today for verification of digital designs. And a UVM environment concentrates the following features: constraint randomization, transaction level modeling, modularization, which means standard objects and components, reusability, and phasing mechanisms, which are built in the verification flow. So because of the advantages of using UVM, it is today the most widely used methodology. So the purpose of this work is to verify a router of Zyna. Zyna is a network on chip. Zyna, it stands for Extensible Interface Network Architecture and is a 2D mesh network on chip, which was proposed by Mello, and it has versions in VHDL and System C. Now, I highlighted here System C because it is the version that was verified in this work. Now, when Zyna was created, it was originally tested with test benches and scripts, but without following a specific methodology like the ones that we have in the industry. So here is when it came the idea to verify Zyna using a methodology like UVM. Now, discussing about Zyna's router, which is the design under verification, Zyna's router has 5 inputs and 5 output ports. The input and output ports are local, 2 local ports to send packets to adapter and the core, and the inputs and outputs to north, east, south, and west. In the picture here, you can see the internal structure of a Zyna's router. Now, the router has input channels, 5 input channels, and 5 output channels. The input channels, they have an input flow controller to receive packets from other routers. They have a buffer to store packets waiting to be sent to an output channel. They have a routing controller to select the output channel following the XY algorithm, which means that the packet must go to the X-axis first and then go to the Y-axis. And in the output channels, Zyna has an arbitration controller to decide the right time to send a packet and an output flow to send packets to other routers. Here is the example of a packet that is sent between routers in Zyna. Now, the packet structure is made by flits, where the first flit will contain the destination address, where the first half will have the address in X, and the second half will have the address in Y, and all the next flits will contain the payload data. In this example, we have 3 payload datas, and they have 32 bits each. In the very left, you can see here that there are control bits. These control bits will define where a packet starts and where it ends. Now, let's discuss about the UVM verification of the router. Here in this picture, you can see the architecture of the environment. In the bottom, we can see here the design under test, which is the router. We can see in the left and right the inputs and output interfaces to connect the router with the environment, and above is the verification environment itself, which is a UVM verification environment. The verification environment created to verify the router is composed by 5 input agents, which will be connected to the input ports of the router, and 5 output agents, which will be connected to the output ports of the router. The input agents, they have a sequencer and a driver, which will be responsible for sending random packets to random addresses in random times. This is the beauty of UVM. And the output agents, they will receive packets and sending them to the scoreboard. The agents will send all packets, both sent and received, from the router to the scoreboard, and the scoreboard will be responsible for doing the comparison between the packets that were sent and the packets that were received. The scoreboard is the most important part of the verification environment. Now, the scoreboard created to this work has several functions, and these functions was created in order to answer 3 questions. Did all the packets reach their destination without data loss and/or data corruption? Is the number of input packets equal to the number of output packets? And the third question comes because the arbiter, as we know in this router, it follows the round-robin algorithm. So the question 3 is the router following the round-robin algorithm correctly during arbitration? As an example of the effectiveness of the verification environment, when we first ran the simulations with the router, the verification environment was able to find a bug that was not previously detected in the test benches of the designer. This bug happened when multiple packets were sent simultaneously. In this case, some of them were being lost or even being sent to the wrong output. Here in the waveform above, we can see a packet that is sent to the output E here, but the packet never goes to output E actually, right? And this problem, the root cause was found and was fixed by the router's designer, and further simulations validated this fix. Here in the waveform below, we can see here the same packet coming from the input W, and as well, the packet should go to the output E. And in this case, the packet goes to output E. Here we can see the packet coming from output E. It was created 2 test cases for this verification. The first test case will send multiple random packets from all input ports to all output ports. And the second test case will send multiple random packets, but for one output only. Well, in the first scenario, what we want to see here is how the router deals when stressed by many packets coming from everywhere and trying to go to everywhere. And in the second test case, what we want to see is how the router deals when multiple packets are trying to use the same output, and how that output deals when stressed by a bottleneck of packets. Each of these test cases sends up to 150 random packets, and after the bug showed in the previous slide was fixed, no other bug was found when running with these test cases and in these scenarios described. So as conclusion, this paper presented the functional verification of Zyna's router. The verification environment created is robust and scalable, and it follows the UVM methodology. And it provides randomization of packets and a strong scoreboard checking. As future works, we propose the integration with a System C simulator in order to collect coverage results, and the expansion of this environment in order to verify the complete network on chip. And thank you very much. Any questions?